afternoon as two co-presenters. So it's going to take me here half a minute to read the bios. The first presenter is June Wu. Dr. Wu is a research scientist at INEOS Composites. She graduated from the Chemical Engineering and Material Science Department at the University of Minnesota, Twin Cities, in 2005. Her research and product development focuses include developing compression mold resin systems for various applications, such as advanced resin systems for EV batteries, enclosures, and low VOC, low odor resins for structural application. Dr. Wu prior industrial experience include developing epoxy vinyl ester resin for corrosion application and polyurethane structural adhesives for the automotive industry. The co-presenter is Hugh McDowell. He's a manager of material development at Teijin Automotive Technologies. He finished his Master of Science degree in Chemical Engineering at Michigan State University in 2016 with a research focus on bio-based polymer synthesis, and has since worked in automotive composites research and development at General Motors and now Teijin. His research has spanned a multitude of fiber and resin types of various composite processes. Currently, he focuses on robust FR and structural SMC composites for EV applications.
Good afternoon, everyone. Thank you for coming in, sitting, listen to the session, and it will come up soon. My name is June. I'll co-present this topic with you together. Thermogravimetric analysis of SMC resins for electric vehicle battery enclosure applications. Okay. I'd like to start a little bit about the background or the motivation for the study. As we all know, SMC materials being used in traditional battery enclosure structure for many years, and with the recent EV electric vehicle industry booming, we noticed there's a lot of attention being put on it, using composite materials to replace metal as EV battery enclosure housing structures. So there are multiple benefits we can get from using composite materials. From the production and processing standpoint, using composite materials have the ability to accommodate complex part designs, which is very typical for EV housing structures, as we've seen today in a lot of the presentations. Also, the cost associated with SMC process is about 20 to 70% lower in the tooling cost, and compare with metal equipment, like stamping equipment for metal parts. And also, SMC process has faster lead time for prototype and production. And for the materials performance standpoint, SMC materials are generally 20 to 50% lower in the waste, and that brings the waste reduction, and also without compromising the equipment, compromising the strength and stiffness. And secondly, SMC materials have excellent thermal insulation properties, as well as electrical, noise, vibration, harness properties. And lastly, SMC formulations is formulation design is very flexible, so that we can achieve various materials performance for to meet the specific applications. So as a resin supplier, INEOS, and Teijin is a SMC compounder. In this study, we want to take a deep dive to look at SMC resins thermal behavior using TGA method. We're hoping the study and the learning can help us and guide us for future formulating work. Okay, the goals of the studies include 4 aspects. First is to investigate thermal degradation behavior of cured liquid resin-only samples. Those are the polymeric components in the SMC parts. And secondly, investigate thermal degradation behavior of cured SMC paste resin, which is ATH field, specifically for, this study specifically for FR SMC parts. So the materials containing, thermal behavior of the materials containing ATH is quite important to be studied. And thirdly, we determine the FR properties of SMC compound samples. And lastly, we look at results of these 3 items and examine the results and try to bridge the understanding from the thermal degradation behavior to the FR properties of SMC composites. So I'll be presenting the first 2 items, and Hugh will present the third and fourth items and summarize the study. So this slide shows the materials we studied, as well as the design of the experiments and testing matrix, to say. For the first item, as we talked about, the liquid resin only, TGA performance, thermal performance. We did the study on that part with sample A, B, and C. So these 3 samples are based on different base resin. As you can see, A sample is based on UPR resin, B sample is based on VR resin, and C sample is based on Electron 2502 resins. These are all combined with the same type of LPA in that first set of study. So the second set of study, we include 2 more samples, sample D and E. These 2 samples are all Electron 2502 based, but we include different type of LPA in there. D sample is polyester LPA, and sample D has polystyrene LPA. So these 5 samples, the SMC paste of these 5 samples were studied by TGA method. So in this set of study, we can see the difference between the base resin, as well as to examine the difference that might come with the LPA, the type of LPA we used in this. And then we did the fire test for all 5 SMC panels. For the people who are not familiar with thermogravimetric analysis method, this is kind of a introduction or brief description. So if you see a really small, there is a really small panel, aluminum panels here. So the small amount of sample is put in that panel, and then lowered down into the during the test is lowered into the heated chamber with controlled atmosphere. It can be nitrogen or just air purge. And there's a fine balance up here to record the temperature, record weight of the sample that in aluminum panel. So at the end of the test, the equipment will provide a weight loss curve as a function of time, as a function of temperature, as shown in the green curve here. And from that curve, we can define the thermal degradation onset temperature. Here you can see in this specific curve, there are 2 thermal transitions occurred. First started at 338, the second started at 450, around that range. At the end of the test, above 800 degrees C, there is a residual weight, retained in the sample, and that's related to the char formation that he will talk about later. The screen curve can be calculated into the derivative weight loss curve, which is shown in blue curve here. This curve gives you a little more details about thermal transition, and it tells you at what temperature the degradation reaction reaches a peak. Yeah, reaction rate reached the peak rate. Okay, so because most of the wave change in our system that I'm studying occurred in the first transition, so we focus on the comparing that first onset temperature and first peak temperature for the samples I just talked about in the study. So let's get into the result. This is TZA weight loss curves for the resin plaques only. As I said, the 3 samples are based on 3 different base resins with the same type of LPA. As you can see, the green curve, which is H250 based sample, has the highest first onset temperature, indicating this liquid resin, this combination has more thermal resistance than the other 2 samples, which is about 50 degree heat C higher than UPR and MER based. And the second onset temperature follow the same trend. So the conclusion here is the observation we made here is initiation of thermal degradation process is resin dependent, and H250 resin shows the highest onset temperature. When we look into the rate of thermal degradation curve, which is a derivative weight loss curve that I talked earlier, as you can see that actually the first transition in sample A and B include multiple small or minor transition that we didn't see in the weight loss curve. But both the cluster, I would say cluster of the first transition temperature is still a lot, the peak rate temperature is still a lot lower than the H250 based, which is around 408 degrees C, and then really clean peak here is just a run thermal degradation reaction here within that first peak range. So the observation here is a peak at the thermal degradation rate temperature is resin dependent. Again, H250 based resin shows the highest peak degradation rate temperature. So what happened if we added ATH into these resins? This is the weight loss curves for all the 5 samples. I talked about with ABC are different base resin, with a different base resin, and CDE with the same base resin but different type of LPA. But with all 5 samples, we can see that the first onset transition temperature is at 250 C. That's actually associated to the ATH decomposition temperature when ATH start to degrade and giving out the water. So that weight loss is associated to the water that coming out of ATH. And then, so the second onset temperature here is actually correlated to the polymeric component we studied earlier. Now you can see that the second onset temperature, the differences between these the ABC is a lot smaller. Recall it was about 50 degrees C in the previous weight loss curves. So that's one observation we made, and we think this the ATH, the addition of ATH impact that thermal degradation behavior of a polymeric material itself. And the next observation we made by comparing CDE formulation, CDE samples, we noticed that the type of LPA seems didn't impact the onset temperature, the onset temperature significantly. So again, the derivative rate of thermal degradation degradation curves of A, B, C, and D. Here you see we can see for all 5 samples that the decomposition peak temperature is around 280 C. That's consistent because of it's related to ATH. And also the polymeric materials degradation temperature shifted again and compared with resin-only samples. Also the differences in the peak degradation temperature are smaller in the paste plaque. That's true for the peak degradation temperature as well as the onset degradation temperature. So that's the TGA result. I'm gonna turn it over to.
All right, so we looked at the TGA curves of the paste only and saw a significant difference between the different resins for onset degradation. That was a little convoluted when we added ATH because of the ATH degradation itself. So therefore, when we went to coupon level testing, we're really seeing if there's any difference on the coupon level between the paste only, as we saw in the paste only, once we add ATH and do an actual coupon level test. So we picked UL 94.5 for that testing. 5EA is markedly harder to pass than like a V0 that you see with a lot of thermoplastics. So that was the main reason for going 5EA. It's also something that we can readily test in-house, and a lot of other people have the same capability too. So fiber buckets were measured for each formulation. The test itself says that an after flame and after glow time more than 60 seconds is a fail. So we debated on whether to do this time-based and really kind of parse different seconds of after flame time, or just go based on the pass-fail criteria. It seemed to be the simplest way to just go purely based off pass-fail criteria. So the results from the study correlate fairly well with the resin-only samples. So in the resin-only sample TGAs, we saw an onset degradation that was slightly lower for the UPR and BER. And even though the UPR, BER, and the Aerotran 2502 all pass for 3 and 2.5 millimeter, as we go to the thinner thicknesses, the UPR and BER start failing. So this follows again the same trend that we saw with TGA. It was a little convoluted with ATH for the TGA paste panels, but we were able to kind of reclaim on a coupon level test. Also interestingly, the LPA differences between PVAC, PE, and polystyrene didn't seem to impact the 5U performance at all. So this gives a lot of design freedom for a formulator to really pick which LPA matches best for either shrink control or other aspects of pigmentation, things like that. Additionally, we looked at Char values. So the hypothesis was that the ATH degradation decomposition was the main FR driver for FR performance. But to just kind of make sure we cross that base, we looked at the Char yields of UPR, VER, and the Aerotran with the different LPAs. All of them were at or less than 2%, so this is pretty insignificant as far as FR performance. So the way that we did this is we did all this in TGA, with a TGA under nitrogen, and then switched to air to see what Char yield happened in that difference. So in summary, the star degradation and peak degradation temperatures were higher for the hybrid system versus the UPR or the VER and the resin-only samples. The hybrid resin peak degradation temperature didn't significantly change with different LPAs, again, relating to that design freedom. Char formation was not a critical FR mechanism for any of the formulation studied, and the results of the 5B showed that the more thermally resistant hybrid resin also performed better than the UPR and VER in coupon level testing. So although the results are important for the formulations that were designed in this test, this is really designed to be a model and methodology of looking at different base resins. So when I'm designing any sort of FR system, I don't need to be as concerned about LPA types. I might not really need to worry about differences between UPR versus VER versus hybrid. Really, I need to look at something that has the highest degradation temperature with a resin only and kind of go from there and pick that way. So I thought that was an interesting result. I think there could be a lot more results, a lot more work that could be done in the same kind of category. We've talked about maybe using cone calorimetry in the future to look at heat release rates and differences between resins. But this is a pretty interesting finding that it makes logical sense that something with a higher degradation temperature would perform better in FR tests, and we were able to see that from a fairly academic bench level test with a very small sample to all the way to a coupon level test. So a few acknowledgments. First and foremost, Laura Lilford at INEOS, she did all the TGA analysis. So I think this study is also a credit to just collaboration, especially during COVID. When this study was kind of first talked about, my lab was actually shut down, so I relied heavily on June and Laura to do a lot of this testing, and it was a really cool way of doing this remotely and also during COVID. Also Tom Skulski for his insights, and Michael Hilton for his insights as well for picking different LPAs to look at and how to design those initial formulations. All right, thank you very much.